So I guess I'm recording. I hope so. Okay, so chapter 3 is what we're going to start out with, and chapter 3 is fairly simple. And what we're going to start looking at with chapter 3 is bonding, which is why I wanted to start chapter 3. This book goes straight into naming, but I really think that kind of does you a disservice without understanding some of the things we're going to be doing. So the first thing, we're studying organic chemistry. And organic chemistry is important, especially for pre-med, because organic chemistry is really the precursor to biochemistry. You can't really fully understand biochemistry without understanding organic chemistry. Of course, in med school, you're not going to ever take organic chemistry. You're going to take biochem. But you do need to know this background information. You won't be synthesizing like we do in class, but understanding reactions is really important. So organic chemistry is the study of organic-containing compounds and their reactions. Specifically, what happens to a molecule during a reaction? Collisions and bonds breaking and forming. That's what we're focusing on. The big question, why do reactions occur? Can we predict when reactions will occur? Can we predict what products we're going to get? And all of those are really important. The main thing is we're focusing on electrons. Electrons have a what charge? Negative. And negative charges are attracted to what? Positive. And what has a positive charge? And where's protons? Nucleus. So what we're looking at is interactions between our electrons on one atom and a nucleus on the other, typically. So that's what we're going to focus on. So, of course, one part about organic chemistry that we need to understand is structural theory in our typical bonding for neutral atoms. So each atom wants to bond, and it wants to share its electrons when we're talking about covalent bonding, which is a bond between two nonmetals. And we want to share electrons, and we typically want to share electrons to get to 8 electrons. But each atom has a certain number of valence electrons, which are our outer electrons. We only really care about our outer electrons because our inner electrons are unavailable. So what we're typically looking at is carbon, nitrogen, oxygen in the halogens. Every once in a while you may see something with phosphorus. A lot of times some of the reagents might have phosphorus in it. Sulfur is also a common one, especially in biochem. Disulfide bonds are really important in biology. So if you ever think about getting a perm in your hair, it smells like sulfur. It's because you're breaking the disulfide bonds in your hair, reforming your hair either to be straight or curly, depending on what you're trying to do. And then the disulfide bonds reform. That's why it smells so bad. So disulfides and sulfur is also really prevalent in chemistry, especially in biochem. So those functional groups are really important. Our common bondings really have to do with how many electrons we have in the valence. Carbon has 4, so it likes to form 4 bonds. It doesn't have to be 4 single bonds, just 4 bonds. It could be 2 double bonds, which we don't see as often. A triple bond and a single bond, or a double bond and 2 single bonds. Either way, total of 4. In our neutral state, nitrogen likes to have 3 bonds in 1 lone pair. Oxygen likes to have 2 bonds, 2 lone pairs, and halogens likes to have 3 lone pairs and 1 bond. In its neutral state, and most atoms want to be neutral as much as possible. So what happens in a bond? This is a representation of how far away our hydrogen molecules are. And basically there's a low point energy where our bonding is at its lowest energy. Meaning, if the hydrogens are too close together, those electrons repel each other. But once they're further away, our hydrogens doesn't have its duet, so it's higher in energy. And this is what it's showing. So covalent bonds is a pair of electrons shared between 2 atoms. And a bond's always going to be a pair of electrons. Most of our atoms tend to bond in a way to achieve an 8 electron valence, so the octet rule. except for hydrogen, which likes to follow the duet rule. It doesn't just like to follow the duet rule. Of course, when we're thinking about what orbitals we have, hydrogen only has a 1s orbital. And how many electrons can be in an orbital at a time? 2. So hydrogen only has space for 2 electrons when it's bonded. It doesn't have space for more than 2 electrons. Most of our atoms, carbon, nitrogen, oxygen, fluorine, they're trying to achieve an octet. But hydrogen is only trying to achieve a duet. And that's its most stable state. It's really light. Oh, there's eye clicker question. So always have your eye clickers out. Okay, so what force is responsible for bonds? Electrostatic. What does electrostatic mean? Electrons are negative, they're attracted to a positive nucleus, electrostatic. And having that octet. So another thing that's really important to understand is the concept of formal charge. Our atoms can have an octet but still have an overall charge. Now the structural theory that we were just looking at, our atoms were all neutral, but that's not always the case. An atom can have an octet and have a charge, and that affects our stability and our reactivity, and it's really important that we recognize that. It's also really important formal charge is always specified when you're drawing an atom that has a formal charge. And when we start looking at nucleophiles and electrophiles, formal charge is really important. So I just wanted to review how to go through and understand formal charge. To calculate your formal charge, you determine the appropriate number of valence electrons in an atom that comes from the periodic table. So in this case, oxygen here should have 6. That's what the periodic table says. Then we determine the actual number of electrons, and you're assuming, and this is going to be different when we talk about oxidation state in chapter 4, but you're assuming that you have a complete sharing of the 2 electrons, meaning in this bond, 1 electron is closer to carbon and 1's closer to oxygen. It's not really what's happening, but that's what we're assuming when we're looking at formal charge. So that's why we look at only half of the electrons in a bond, but we look at all of the electrons in lone pairs because they're only associated with that atom. So carbon, oxygen, 1, 2, 3, 4, 5, 6, 7. Then we just subtract our periodic table number from our valence electrons, and that becomes our charge. Now, if you'll forget whether you put your periodic table number first or the one here first, electrons give you which charge? Negative. So if you have more electrons when you count this, should you have a negative number or a positive number? Negative, because electrons are negative. So if you ever forget whether the periodic number goes first, if you have more electrons here than what you actually counted on the periodic table and your number comes out positive, you did something wrong. The electrons are negative. So you have more electrons than you should have a negative formal charge. It is uncommon, though not completely ever going to happen, but it's uncommon for most organic compounds to have more than a negative 1 or a positive 1 charge. There's exceptions, NO2 is an exception, but in general, it's too unstable to have more than just a negative 1 or a positive 1. And you won't likely ever see carbon with more than a negative charge or a positive charge. You won't ever see carbon with like a +2 because it's just unstable. It's too high in energy to actually exist for any long enough given time for us to care about what it does. Now, realize when I say it doesn't exist, it doesn't mean that for a fleeting moment it might exist, but we don't care because we can't measure it and it won't have an effect. It'll be negligible. So, oh, and I didn't go through Lewis structures because you should have done that in the general chemistry portion. But you do need to know Lewis structures to figure out some of these answers. looking for one. So, you actually need to know how to draw this. And this should be your Lewis structure. And nitrogen has a zero formal charge. Trick, carbon, when it has 4 bonds, is always going to be neutral. You can calculate it, but it's never going to change. And this carbon has 4 bonds. Hydrogen should only ever have 1 bond. It can be positive when it has no electrons around it. It can be negative, but only if it's bonded to something that's much more electropositive, like a metal. But typically you'll see hydrogen as positive in a lot of systems. Now, most carbons will have 4 covalent bonds and no lone pairs to avoid carrying a formal charge, but they can't exist with a formal charge. One example is a carbon with a positive charge, and that is what we call a carbocation. Carbo for the carbon, cation because ion. Cation means positive charge. Now, you do have 3 valence electrons, and you have a total of 3 bonds. Remember, we don't typically draw the hydrogens, and that's the case here. So you need to recognize that when a carbon has a positive charge, it has 3 bonds. It's oriented to be trigonoplanar, which is very important for some of the reactions, especially substitution reactions. So this is what our carbocation looks like, and you should recognize it has how many hydrogen atoms it has. Again, carbon will unlikely ever carry a positive 2 or positive 3. It's positive, it doesn't want to be more positive. In fact, this carbocation we talk about like it exists, but it's actually not even able to be measured. So it's not even measurable. Now, again, you can also have a negative charge on carbon. What do you think this is called? A carbanion. Now, with a carbanion, you're going to have a lone pair. You should never draw a lone pair on carbon unless if you draw that negative charge. And you should never have a carbocation that doesn't have the positive charge drawn, because then you're assuming how many hydrogens it has. Just like the carbocation, the carbanion has only 3 bonds, but it has a lone pair instead of an empty p orbital. So its 4th orbital is holding the lone pair. You have to show any formal charges that are drawn. Now, of course, in the MCAT, it's multiple choice. You won't be drawing those out. But if you have to figure out a reaction mechanism to find a final product, you need to be able to understand these. Covalent bonds are electron pairs that exist in an orbital shared between 2 atoms. But our covalent bonds aren't exactly all equal, and it really depends on electronegativity. So we have 2 classifications. We have nonpolar covalent, where bonded atoms are shared equally. And we have polar covalent, where one of the atoms attracts electrons more than the other. Of course, we have ionic bonds, which are between metals and nonmetals, but it's the same force that's occurring, meaning the electronegativity is so big between metals and nonmetals that instead of sharing electrons, one would rather donate and the other would rather receive to form a full charge. But it's the same concept. Our polar covalent just aren't as big of a difference in electronegativity, so they still share electrons. So electronegativity, this is something that's really important. It always increases to fluorine. Fluorine's our most electronegative atom. This is not, of course, the whole periodic table. We don't really care about anything that we're not showing here. This is what we call the organic chemist periodic table. We're seeing all the things that we care about. Notice, even though hydrogen is on the periodic table typically over here, its trend with electronegativity is closer to between boron and carbon. And carbon-hydrogen bonds are always considered nonpolar. In general, and this isn't cut and die hard rules by any means, but in general, nonpolar covalent, you have a small electronegativity difference. Polar covalent is about between 0.5 and 1.7, and ionic is greater than 1.7, though honestly, there's some ambiguity with some bonds, and throughout organic chemistry, you'll see some reactions where a bond, a reagent has, say, a magnesium and a bromine, and we sort of draw it as a ionic bond sometimes and a covalent bond other times because it's kind of at that 1.7 mark here or there. But our polar covalent have larger electronegativity differences. Pretty much carbon and hydrogen are non-polar, but carbon and nitrogen are polar, carbon oxygen are polar, carbon fluorine is polar. Will your electrons in a polar bond be closer to a electronegative atom or the more electropositive atom? Electronegative. Electronegativity is how strongly the atom attracts the electrons. So, if we have a carbon-fluorine bond, the electrons will be much closer to the fluorine, which causes a difference in charge. And that difference in charge, because the electrons are closer to fluorine and farther away from carbon, means carbon's going to have a partial positive charge, and the fluorine's going to have a partial negative charge, and that's always going to be true. Because that electronegativity difference always exists. Even if, say, the fluorine had a positive formal charge, it would still have a partial negative charge because of electronegativity. A positive charge on fluorine, not stable, but if it's, say, it did happen, you still have a partial positive charge. And remember, the reason why is because your nucleus is positive. So if your electrons are closer to the fluorine, your carbon's going to have a partial positive, and your fluorine's going to have a partial negative. And that doesn't ever change. It's part of that bond. So that brings us to chapter 3, because I haven't actually gotten there yet. I wanted to go through some of the background stuff that the book doesn't cover, because I feel like if I don't, it can get real confusing really fast. And then that's really fast going through some of the background stuff. So, atomic orbitals, and you probably went a little bit through this in the general chemistry portion, but we'll just summarize what we care about in organic chemistry. So, the theory matches with experimental data that electrons can behave as both particles and waves. So here's a wave function. A wave can have a positive portion and a negative portion. What's really important when we're talking about these orbitals to remember is we're not talking about charge here. We're just talking about solving an equation, where solving the equation can give you a positive number or a negative number. That's really important because we talk about charge so much in this class. When we're talking about orbitals, that positive part and the negative part isn't representing charge. It's just representing whether we're up or down with the wave. Which is why, from now on, pretty much we'll show blue and red. Sometimes you'll see shaded and unshaded to represent the two different charges. And it's irrelevant whether you're talking about a positive or negative. So psi is what we call our wave function. So it's a big equation. We're not going to go through it. And then where our wave crosses the 0 point, that's our nodes. And the node is a 0 probability that the electron would be in that space. So what we're trying to do with the wave equation is using mathematics and probabilities to get an idea of where our electrons are in a molecule. And when we get an idea of this, then we can understand some things with reactivity. So the wave equation was developed. It's all long. We don't care. The wave function describes the area where the electron can be found in relationship to the nucleus. Now, it doesn't specify the exact location of the electron in the orbital, but gives a probability of knowing where it is. So, if we solve for that equation, which we're not going to, we can get 4 solutions. And these values are what are our quantum numbers: N, L, ML, and MS. So this finally comes to some of our summaries. So, Megan, what does N stand for? And what does it describe? And what possible values can it be?
0 to infinity.
Yeah. Now, we won't ever be looking on against them, but in theory. Victoria G. What does L stand for? Some dude's name. What does it describe? Yeah, so we'll be looking at that. What's the possible value? Yeah. ML, Jocelyn. And what is that telling us?
It describes the representation and then the orbital level.
Yeah. And then Sky, what does MS tell us?
The spin quantum number describes the spin up or spin down.
Yeah, spin up or spin down. So let's look at these in a little bit of detail. And it actually makes a bit of sense when we think about what we're looking at. So every quantum number describes an allowed energy state for the electron. And what's important is, say we take carbon. How many electrons, according to the periodic table, does carbon have? Total. Not just valence, but total. 6. Each electron is going to have a different set of these 4 quantum numbers. Meaning there's a different place in the orbitals we can put them in. And that tells us a lot about our carbon. Now we only really, when we're looking at bonding, care about our valence electrons, but to understand where our valence electrons are, we have to understand where all electrons are. Now that doesn't mean each of these 4 numbers are going to be different, but each electron has these 4 numbers, and all 4 of them will not be exactly the same for each. So N again is a principal quantum number, and it indicates the energy level that electrons occupy. N has whole integers. It's not going to be 0.5. It's going to be 1, 2, 3, 4. And this level is known as our shell. So N equals 1 is our lowest energy level. 0 would be the nucleus. So N equals 1 is our lowest energy level. N equals 2, etc. And we can use the periodic table to look at that. And as we increase in that energy, that number, our energy increases. Now, carbon, nitrogen, oxygen, fluorine, what row on the periodic table are they in? They're in the second energy level. So their energy number, their N, the highest energy level is going to have is 2. But it's also going to have a 1, because it has to have a 1 and a 2. But the most it's going to have is a 2. When we get higher with 3 and 4, but we won't really care about those as much in this particular class often. There's some cases where reagents use metals that have higher energy levels. And again, phosphorus and sulfur is sometimes talked about, which are in, of course, 3. But we usually care about 2. L is our angular quantum number, and it indicates our shape. When L is equal to 0, that's our s orbitals. When L is equal to 1, that's our p. When L is equal to 2, that's our d. L, though, can only be 0 to n minus 1. So, if we only have 2 for carbon, we can only ever have 0 and 1, meaning s and p orbitals. We don't ever have d orbitals the d orbitals are higher in energy and we don't have any electrons there. So for carbon, what we care about are s and p, and we'll see that. S and p, it's been a long day. I teach all day on Mondays. This is rough. So s and p. So that's all we ever really are going to care about. But again, d is going to be important sometimes. ML is our magnetic quantum number. It indicates the area the electron occupies. And values of L are determined by our positive and negative values of L. So for example, if L is equal to 0, well, we don't have a positive and a negative value of 0, so ML is equal to 0. So what does that mean? We only have one s orbital at each energy level. Because, again, the ML is determined by our L, and if L is equal to 0, that's our S. So that's what we just said. So what we see here is when n is equal to 1, we're starting to put this together. then of course our L can only be equal to 0 because L is 0 to n minus 1. N minus 1 is 0. So at our principal energy level, we only have an s orbital. That is why hydrogen, again, only has our one s orbital. And it can only have one bond, because each orbital can only hold 2 electrons. So it only has a 1s orbital, and this is the only orbital it has, and L is 0. So that's why each s orbital only has one energy level. Then in 2, we have the possibility of an L equals 0 and an L equals 1. Because again, L is equal to L is equal to n minus 1. So 0 and 1. So that means that we also have a 2s, and then we have 3 degenerate p orbitals, where ml is equal to negative 1, 0, and positive 1. This is what our quantum numbers look like for everything in our second row. Now the amount of electrons is dependent on how many electrons the atom has. So carbon has 6 electrons, and this is what it looks like. P's are higher in energy in S, and we'll talk about that with the shapes in a second. But this is what we're basically looking at in organic chemistry. And of course hydrogen, which only has the 1s. Nitrogen, oxygen, fluorine have these same energy levels because they're all in n equals 2, but they have different number of electrons when we fill them in. Now this lets out our spin, which of course is that last one. Now when n equals 3, we also have our 1s, our 2s, our 2p orbitals, and then we have our 3s, our 3p, and then lastly, of course, we have L equals 2, which my thing is in the way. When L equals 2, then we can have an ML of negative 2, negative 1, 0, positive 1, and positive 2. That's why our d orbitals have 5 degenerate orbitals. When your orbitals are the same energy level, we call them degenerate. So all 3 of these are degenerate because they're the same energy level with each other. Now MS is the last one, and that's why each of these won't have the same 4, because in each orbital you can either be spin up or spin down. So these 2 electrons have the same N, L, and ML, but this one has a positive 1/2 and this one has a negative 1/2. These 2 electrons have the same N, L, and ML, but again, positive and negative, and so on. So they won't all have, none of them are going to have the exact same number. Now let's look again at what they look like. So an s orbital is our lowest energy level, with a principal energy level of n. And our s orbital is pretty much a circle. So it's a spherical shape around an XYZ axis plot. Our 1s orbital doesn't have a node. Our 2s orbital has a node on the inside that you can't really see. That's why our 2s is higher in energy than our 1s. But it's a spherical circle. This will be important when we talk about our hybridized orbitals. Now again, we have our 3 p orbitals. And our 3p orbitals are going to be, again, degenerate, but we typically draw them on 3 axes. Our x-axis, our y-axis, and our z-axis. And those are our 3p orbitals. So it's really important to understand that those 3p orbitals, that's what they look like, because we'll be looking at those in more detail. These, we're not going to talk about that, but there they are. Again, we won't really be using d orbitals. S, also, we're not going to be talking about that, really, for anything in here. Another thing that's really important to understand is everything in the second row can't have more than 8 electrons. Because we can't fit more than 8 electrons in our orbitals, in our valence. So our valence is our 2 level. This isn't our valence. And if you look at our second energy level, or our second n equals 2, we only have 1, 2, 3, 4, 5, 6, 7, 8. Room for 8 electrons. So carbon will never have 10 electrons surrounding it. Nitrogen will never have 10 electrons surrounding it. Because there's no room for them in the valence. There's only room for 8. Things like sulfur and the 3 energy level, they actually do have those d orbitals. We don't really care about, but they're there. And because those d energy levels, if you look back at, if we look back at the way these energies are drawn, way over here, here we go. As we get higher in energy level, our difference between our level gets smaller. That's why we can have an expanded orbital for things like sulfur, anything past 3. Because they're closer and it's easier to just throw an electron up there. But for 2, it's too far away from that n equals 3 for it to excite an electron up there. So we won't ever have more than 8 electrons in a carbon bond. So never draw more than 4 bonds to carbon. Ever. Oh, well, there you go. If an electron is in the n equals 4 shell and the L equals 2 subshell, how many possible combinations of quantum numbers does it have? And if you're paying attention, I kind of threw the answer up there. So the answer is 10, which I went a little fast there. But why? So remember, first off, we know it's in n equals 4. So we know it's in n equals 4. So L equals 2. We know that too. Our ML is negative 1 to 1. So that means our ML is those 5 d orbitals. Negative 2, negative 1, 0, 1, and 2. But in each of those degenerate 5 orbitals, we can have spin up or spin down. So, because of that, we have 10 possibilities. So 5 spin up and 5 spin down. And of course, we were told it was n equals 4 and L equals 2. So we were told some of that. Okay, so our atomic orbitals in more detail. Again, because of that wave function, here's our p orbital. Our p orbital is going to be really important to carbon. Now, this is our p orbital on the y-axis, but of course we know we have 3. Now, the p orbital is higher in energy than our 2s orbital because of this node. So a node is 0 probability that the electron's going to be there. So anytime you have a node, you're going to have higher energy. The more nodes you have, the higher in energy. Because the less space your electron has, the less stable it's going to be. We'll see that with resonance. With resonance structures, we have more resonance structures, the more stable the molecule. So because it has this node, that's why our 2p orbitals are higher in energy than our 2s orbitals. Of course, all of our 2 orbitals are higher in energy than our 1s because 1 is a lower energy level. That does get ambiguous when you get higher than n equals 3. N equals 4, some of your levels are getting mixed up with each other. But when we're low enough, like n equals 2, we don't have any mixing of our 3 energy level, which is why, again, we can't have more than 8 electrons. So for a valence bond to occur, we need to have overlapping of orbitals. And there's 2 ways our orbitals can overlap. They can either overlap with constructive interference, where our like portions overlap together, meaning if we're bonding 2 p orbitals, the red part and the red part are going to bond. Or the blue part and the blue part is going to bond. The other way is the blue part trying to bond with the red part, and that's destructive interference. We have to have bonding to occur. We have to have a bonding orbital. When we get this destructive interference, it's going to be higher in energy than our constructive interference, which is, and again, it doesn't matter if we're talking about the positive sign of the mathematical function or the negative. What matters is the likes have to interact. Again, this isn't charge, so it's not like when we talk about charge that positive repels negative. This is a mathematical function, which is why I rather use the colors than the charge. So red needs to overlap with red, or blue can overlap with blue for it to be constructive. So only constructive interference will result in an overall bond. Now, that brings us to our types of bonding. We have two types of bonding. First off, all covalent bonds contain 2 electrons. It's very important. Only 2 electrons are allowed in an orbital. See? Each orbital, even the degenerate orbitals, each only have 2. So only 2 electrons are allowed in an orbital. So only 2 electrons per bond. So we can have a sigma bond, where our molecular orbital is formed by a head-to-head or tail-to-tail overlap. This is showing 2 p orbitals overlapping, but it could also be 2 s orbitals. It can be an s and a p, and it can be our hybridized orbitals, we're going to talk about in more detail. But overall, it's a tail-to-tail or head-to-head. So that means that we have these types of covalent bonds, and these are where we're sharing the electrons. All single bonds are sigma bonds. And all covalent bonds have at least 1 sigma bond. You have to have a sigma bond to have the next type of bonding interaction we're going to talk about. You can't have it without a sigma bond. So the next type of bonding interaction is a pi bond. And this is with 2 unhybridized p orbitals. That's really important. It has to be unhybridized p orbitals. You can't have an effective pi bond if the p orbitals are not unhybridized. That line up in a parallel way, like this. Now, it's untrue to say that the electrons are shared here and not here. They're actually shared in both, but it's hard to represent that in a 3D structure. But the probability is the electrons are shared here. So the way this is drawn with the 2 electrons just in this orbital is kind of ambiguous because it's hard to fully draw it the way it actually exists, which is not saying the bond is on top or on the bottom, but it's between these 2 p orbitals. You cannot have a pi orbital without a sigma orbital first. I mean a sigma bond first. This is our sigma bond. But we're not focusing on it, but we have it. A double bond has a sigma and a pi. A triple bond is a sigma and 2 pi bonds. Now this is only showing the 1 pi bond, but we'll look at that in more detail. So one thing is the more bonds, the shorter. Oh, I have the shorter text. The more bonds you have, the shorter your actual bond. And we'll talk about why that is, so we'll have to look at hybridization. So I don't really have this on here, but it's kind of integral. There's 2 ways our bonds come together. Again, that constructive interference and destructive. And we call those types of interactions bonding and anti-bonding. That makes sense. So which one's more stable, bonding or anti-bonding? And which one has higher energy? When I say higher energy, am I talking about it being more stable or less stable? Less stable. Anytime I talk about higher energy, I'm talking about less stable. It's really important as we talk about these things. So here's a real simple example. How many sigma bonds and pi bonds are in the following compound? the answer? Anyone? So every single bond is a sigma bond. But what am I not showing? You have to consider your hydrogens also. Woo. Sorry. I talk loud enough without that. So how many sigma bonds do we have? We have 6. And how many pi bonds? 1. So one of these, and if we show there's just 2 bonds, we recognize as chemists that one of those bonds is sigma and the other bond is pi. But they're not drawn any differently when we draw them in our normal skeletal structure. So as far as sigma bonds and pi bonds, when we're looking at strength, we have some differences. So from reading, Victoria M., what are our differences between our sigma bonds and our pi bonds? Or some differences? Mm-hmm. It's another big thing. They do look different. They're bonding, that P overlap. That P overlap means that our double bonds and our triple bonds can't freely rotate. Because if they rotate, their P's are no longer overlapping. So what that means for the structure is that double bonds and triple bonds are more rigid because they can't rotate. So if a double bond is fixed in one position, it can't rotate to the other, and rigidity is brought into the structure, which will make a huge difference in physical properties. So it's really important we understand that. The more bonds between an atom also result in a stronger bond. So single bonds are not as strong as double bonds, and triple bonds are the strongest. However, what's really important is that when we look at reactions, pi bonds react much more readily than sigma bonds. So what is Dr. Cortez talking about? That doesn't make sense. How can triple bonds be stronger but they react more readily? Pi bonds aren't nearly as strong as sigma bonds. But when we're talking about the strength of the bond, we're talking about the total strength of the bond. So what we measure that with is what we call bond association energy. And bond association energy assumes full homolytic cleavage, meaning we fully break the bond between carbon and carbon. In this case is what we're showing. So our bond association energies for these three, as you can see, the sigma bond is only 83, the pi bond is 146, the double bond, and the triple bond is 200. However, if we look individually, this total bond association energy is coming from the 83 from the sigma bond and 63 for the first pi bond. And if you notice, it's easier to break a pi bond. And here, we're looking at 83 for the first sigma, plus our sigma 63 for the first pi, plus our 54 for the second pi. So electrons in our pi orbitals are much more readily available for reactions. It's easier to break them. And typically, we're not breaking both the pi and the sigma in most of the reactions where we're using a double bond. A lot of times we're retaining the sigma bond. So you have to understand that when we're talking about bond strength. Overall, the more bonds you have, the stronger, because it takes about 83 kilocalories to break a sigma bond in all three. And then it's more to break the others. But most reactions, we're not fully breaking all three of those bonds. Now, why might p orbitals be more accessible? Anyone have any guesses? It's more outer. Your sigma bonds is that head-on interaction and it's inside. The p orbitals are outer. And we're still retaining a sigma bond. Now, we can break sigma bonds in reactions. We do all the time. But a lot of times we'll see pi bonds can be nucleophilic, they can be reactive. So that's why. So realize when we talk about bond strength, it's additive. This is another clicker question. So why is a single bond stronger than a pi bond? Oh, I shouldn't have put this one here because we haven't talked about hybridization yet. So, besides the fact that our pi bonds are more accessible because they're more on the outside, because of that head-on overlap, our s orbitals are actually overlap more than our p orbitals. And that's going to create a stronger bond also. So the more overlap, the stronger the bond. And we'll see that even with compounds that that still have an overlap, but maybe not a good overlap. For example, if we're trying to bond something that has like a 4 in energy level, or one of our smaller things with only a 2, we might not get very good overlap. And we'll see that. We won't really be probing too much into that in this class. I probe into stuff like that in my advanced organic. So hybridization is really important. It turns out that, of course, our carbon wants to find 4 single bonds. If we look at this, which is what I drew earlier, we only have 2 available electrons, but 4 of them want to share. So what we typically can think of is, okay, we excited one of these 2 S's into a 2p. So now we have 4 available electrons. However, those 4 available electrons are not in degenerate energy levels. And what we know from geometry and from experimentation is that we have about a 109.5 degree angle between each of our carbon single bonds, and each of our carbon single bonds are equal. So if they're equal, this doesn't make sense. So this doesn't make sense as far as geometry, which states that our 4 atoms want to be as far apart as possible. So that's where that 109.5 degree angle comes from. So that doesn't make sense that way. So what actually occurs is our orbitals undergo hybridization to form 4 equal atomic orbitals. Again, this is a mathematical representation that was figured out and agrees with what we see experimentally. You can by no means physically see this happening with like a microscope. This is a mathematical representation that we know occurs because it agrees experimentally with what we see. So this wasn't just something that came out of the blue. This is some chemistry people that saw these things happening experimentally and did a bunch of math to model it. So first off, I want to preface that. So what do we mean by hybridization? If we want 4 equal bonds for 4 single carbon bonds for each carbon, then we need 4 equal orbitals. So what we form is what we call sp3 hybridized orbitals. What is that? First off, let's forget about our 1s. This is our inner, so we don't care. This 2 is our in quantum number. I won't be discussing it. And what I'm saying, sp3 is 1, as in numerically, 1 s orbital mixed with 3 p orbitals. Again, that 1 I'm using is not the n, it's just the amount of s orbitals. So 1 s orbital mixed with our 3 p orbitals forms our 4 degenerate sp3 hybridized orbitals. They're a hybrid between s and p. Now, do you think that hybrid is going to look more like p or more like s? Why? Yes, exactly. Just like any hybrid, it looks more like p because there's more p orbitals. This is what our hybrid orbital looks like. It has a little shorter of an end and a bigger end where the s mixed with 1 lobe. I'm showing it where the red s mixed with the red lobe. You could also show it where the blue s mixes with the blue lobe. Is the same thing. Doesn't matter. So this is what our 4 degenerate sp3 orbitals look like. And of course, this is one carbon with only 1 of those. There's 4 of them. They're going to be equal, and they're going to be in those 109.5 degree angles. So this forms our 4 single bonds. What we say when we describe this Instead of talking about more S or more P character, instead of talking about more P character, we talk about S character. This one has little S character. There's only one S for 3 P orbitals. So it looks more like a P. Next, we want to consider ethylene. Ethylene, now we have 3 sigma bonds instead of 4 sigma bonds. So how many degenerate orbitals do you think we're going to need? We have 3 sigma bonds. How many degenerate orbitals will we need? 3. We have 3 sigma bonds. And what's a pi bond? What type of orbital? What type of P? Unhybridized. It's a normal P. So we need 3 hybridized sigma bonds because we have 3 sigma bonds. Now I've talked this carbon. This carbon also has 3 hybridized sigma bonds. But let's just focus on one carbon. So how does that look? Well, now we're just going to mix our S with 2 of our P's. And that's our sp2 orbitals. And now we have 3 degenerate sp2 orbitals and 1 unhybridized p orbital. And what's going to form our sigma bond? These. What's going to form our pi bond? This guy. So we have 3 sigma bonds. We need 3 sp2 orbitals. Do you think that's going to look more like S or more like P? Still a bit more on the P side, but more like S than our sigma bonds for our sp3. So we say this has more S character. This is what it looks like. There's one sp2, another, and another, and then our unhybridized p orbital, which is why these compounds form trigonoplanar, where these are planar. So when 2 of these come together to form a carbon-carbon double bond, we have overlap of one of our sp2 orbitals here, and we have our pi bond. Then, of course, this carbon has 2 hydrogen bonds, so that's also an sp2. In this case, overlapping with our hydrogen. So sigma, 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 pi. What about a triple bond? Oh, and again, sigma bonds don't have free rotation because then we'd lose that p orbital overlap. So they're more rigid. What about a triple bond? How many hybridized orbitals do you think we need here? 2. How many sigma bonds do we have? 2. If we mix 1 p orbital and 1 s, how many unhybridized p orbitals does that leave us with? We started with 3 p orbitals. We mix 1 p orbital with 1 s, so how many unhybridized do we have? 2. That's what we need to form 2 pi bonds. 2 p orbitals. So here we're mixing just 1 s and 1 of the p's. These are lowered energy. Oh, and these are lowered energy because these have a full dome. Also, if you're mixing an S, which is low in energy, with a P, which is higher in energy, your degenerate energy is going to be somewhere in between. So your SP, your hybridized SP3, SP2, and SP are going to be lower than where your P was, but higher than where your S was because, you know, it's the average. So now we have our sp orbitals, and we call this having the most S character because, of course, it's less P than the other ones. So it's going to start looking a bit more like our S orbital. Then we have our 2 p orbitals, and again, here's 1 p orbital on one of the axes. We'll call this the Z, and then our Y. And then here's our sp. Now, here's another thing to understand. If we call a carbon sp hybridized, that means this is sp and this is sp. If we call a carbon sp2 hybridized, that means this is sp2, this is sp2, this is sp2. A carbon can't have both an sp3 hybridized orbital and an sp2. It can only be one of those 3. So I always get confusion there. So this orbital is sp2, That means this orbital is sp2 and this orbital is also sp2 that's binding with these hydrogen. However it's bonding with, you're bonding with another carbon. But either way, this sp2 orbital has 3 degenerate. So when I talk about the length of the orbitals in a second, I want you to understand that if it's sp2, all 3 of those have that length. If it's sp3, all 4 have that sp3 length. If it's sp, those 2 sigma bonds are going to have that length. And because of this side-by-side overlap, again, with the pi bonds, we can't have free rotation. So this one wants to know the hybridization of carbon 9. This is never in a good position. Oh, and this is cocaine, in case you were interested. So not good. Oh, did I? Sorry. I don't know. Sometimes it. Just do it again. I must have pressed a button. I can put it to where you can actually write in your answer, but that takes too long. I tried it once for a class. It didn't work out well. Never again. Took forever. Anyway, carbon 9. So it is 4 single bonds. It's going to be sp3. So 4 sigma bonds. Here's another one. Now, I drew HCN for you earlier. So think about what that looked like. Okay, so first thing is, what does HCN look like? What type of hybridization is that carbon? SP. It has a triple bond and a single bond. So it's SP. It has 2 sigma bonds. So if it's SP, that means it must be 50% S and 50% P. Figure out what these are for your rest of your orbitals. You should understand. Oh, and we did that. And sp2, what is it? It's on 3.3. So what's sp2?
33% S.
And 67% P. And sp3 is?
25% S.
Yep. So when we say sp is more S character, this is why. sp3 is only 25% S. So that's a common terminology where we describe things based on S character. So here are our bonds, and let's talk about their differences again. We already know our bond strength. We've talked about this. But what about our bond length? As you can see, a single bond is going to be longer than a double bond. And then the triple bond's the longest. I mean the shortest, sorry. The book simplifies it by saying the more bonds, the shorter the bonds. But that's not really what's going on. What's really going on, an organic chemist knows what's really going on. Sure, there's multiple bonds, but what's really going on is the S character. Again, sp has more S character. What does S look like? A circle. So, a carbon triple bond is 2 of these lined together. These are shorter than an sp3 because it has less S character. So it's a longer bond. And your sigma bonds are your head-on bonding. For it to get a good bond, you need good overlap. So if these 2 come together and they overlap, it's going to be a shorter bond. Because remember, your pi is just that side by side. So your length is really determined by your sigma bond. Which is why I want you to think about Bless you. So here's our sp2. So we know that one's going to be in the middle. We know this is our shortest, this is our longest. What about that bond? Where do we expect that bond to be? It's not going to be as long as this one. And the reason why it's not going to be long as this one is for exactly what I said. If this carbon is sp2, that means this bond is sp2. This hydrogen bond is between an sp2 and an H, so S of the hydrogen. And this bond is between an sp2 and an sp. That means we're taking two shorter orbitals and bonding them. So even though this is a single bond, it's not as long as a normal single bond. Does that make sense? Because this carbon, if this carbon's sp2, all three of those sigma bonds are that length. And you should know that one because that was one of the questions on one of my tests. So, oh, it was a bonus, but still. So realize that not all single bonds are even exactly the same because it's really dependent. Now, is it a huge difference in length? Not necessarily. This is a much shorter distance because you have two sp2 orbitals, and they're both, the same distance. But we do see a difference away from that 1.53 angstrom normal sigma bond of a single bond there. There's also some other things at play, mostly resonance is the other thing to think about. For most of our considerations with organic chemistry when we're explaining stuff, we use both molecular orbital theory, this, and electronic theory, which a lot of times has to do with resonance. And most of the time those two things agree, though they're just two slightly different ways to explain something. So that brings us to molecular geometry. We haven't gotten there yet. So that brings us to molecular geometry. I just want to go through really quickly. Molecular geometry, it's easy for carbons, but you can also determine your molecular geometry for other atoms. And in general, your Vesper theory for electrogeometry is saying atoms don't want to be super close to each other. They have electrons that are surrounding them, and electrons repulse each other, so they want to be as far apart as possible while still retaining overlap to have the bond. So basically, what we can use is steric number, which is really just counting our number of sigma bonds in our lone pairs so we can understand how many orbitals is surrounding the atom. So for carbon, of course, 4 single bonds. We have 0 lone pairs and 4 sigma bonds. For nitrogen, we only have 3 sigma bonds, but we have a lone pair, and that lone pair has to be in an orbital. So we have 4 orbitals around nitrogen. So its steric number is also 4. When we're talking about steric number, we're just looking at the number of orbitals. And where for oxygen, we have 2 sigma bonds and 2 lone pairs. So again, our steric number is 4. This is just the concept of there's 4 atoms, or 4 specific orbitals surrounding those. Now they're going to repel each other. So how does that come up with our steric number and hybridization? If our steric number is 4, it's sp3. All of these are sp3 hybridized. If our steric number is 3, it's sp2 hybridized. A carbon with a double bond only has 3 sigma bonds and 1 pi. So its steric number is 3. And then if it's 2, then it's sp hybridized. A carbon with 1 triple bond and 1 single bond only has 2 sigma bonds. Now, how does that break up? There's one more thing to think about. For carbons, it's fairly easy. If our carbon is 4 single bonds, it's going to be tetrahedral. If it has 3 sigma bonds, so 1 pi bond and 3 sigma bonds, it's trigonoplanar. And it's going to be linear if it has a triple bond and a single bond. Triple bonds should always be drawn linear. But our other atoms are a bit more confusing. For example, nitrogen has that lone pair, and lone pairs tend to repel. I didn't know. Apparently, I hid that slide. Or I did. I don't know. So because lone pairs repel, it pushes the other atoms closer together. So instead of it being tetrahedral, it's a trigonopyramidal. And oxygen has 2 lone pairs, so it's bent, because it has 2 lone pairs that repel even more. So when we look at the molecular geometry, we need to know how many lone pairs are there, but our geometry of our molecules are affected by the lone pairs if we don't draw them. The other option for bent is something that has a steric number of 3 and 1 lone pair. Will also look bent. So those are important to understand. But our normal carbon are those. Now carbon has bonded like this. What steric number do we have? So what hybridization is it? Yeah, it's also sp. We won't see this carbon very much. It's not very stable, but it could exist, and it's going to be sp, and it's going to be linear. That's the only variation that we didn't talk about as far as carbon. Start. Oh, shoot. Come on. I'm trying to start it. There we go. It started. So BeH2 is sp because Be only has 2 electrons in its outer energy level. So it only forms 2 bonds. So it's sp. It has 2 steric number. And it doesn't have any lone pairs. Another thing I wanted to touch on that the book doesn't really touch on is molecular polarity. And I'm not going to touch on this for very long. We already talked about polar bonds. But a molecule can have polar bonds and not have an overall molecular polarity because polarity can cancel out. That doesn't mean that this carbon isn't super electropositive, but we're talking about our overall polarity. Because that carbon is going to be pretty electropositive. It has 2 chlorines attached to it. So when you're looking at molecular polarity, you have to look at both your magnitude and direction. So for example, dichloromethane. They cancel each other out somewhat, but not completely. And we have an overall dipole. Yep. Oh, I thought your hand was up. Lone pairs do have an effect on molecular polarity, but they're separated by the nucleus by a good bit of distance. So there is a dipole moment associated with it, and it contributes to the magnitude, but not so much to direction. So lone pairs are a little odd there. But it will contribute to the magnitude. So we do have a net dipole in both NH3 and H2O. So that was my molecular polarity in this particular question. Which structure has the correct bond dipole found? And I took these from a MCAT practice test, so it's not as clearly drawn as I'd like it to be, but so with your dipole moments and your both molecular and bond dipole, your base is from the more electropositive atom, and your arrow is always pointing towards the more electronegative atom. So this is the important one. Carbon and hydrogen are considered basically nonpolar, so they don't have a dipole associated with them. It's such a small difference that we don't consider it. Here's another one. Which of these 3 contain a net dipole? So again, number 1 is only carbon hydrogen, so no net dipole. Number 2 and number 3 both have polar bonds, but number 2 completely cancels out because of the tetrahedral geometry. So only number 3 has a molecular dipole. Now I'll warn you, if one of these is something like hydrogen, you're going to have a dipole. A bromine doesn't have the same dipole as a chlorine, so it won't cancel out completely. But those are three of the exact same. And again, that's kind of more, that's all you need to know, I think. I don't think we need to go more detail. Another thing I wanted to touch on in this chapter that the book doesn't was intermolecular forces, but I'm not going to spend a lot of time on it because we're running out of time today and I want to finish chapter 3. But apparently I'm going to have to go faster because we have a lot to cover. So a lot of times the book, or a lot of times the MCAT is going to ask you about solubility, boiling point density, states of matter, melting points, and this is especially important in characterization and separations, which is one thing we'll look at later. So intermolecular forces are attractions between molecules. And there's three types of forces that we need to consider. Dipole-dipole interactions, hydrogen bonding, and London dispersion forces, or dispersion forces. And not only understanding those three types of bonding, but also understanding the strength of them. So London dispersion forces are the most weak forces. Every organic compound has London dispersion forces, but it only really matters in compounds that mostly only have London dispersion forces. And it's just a dipole that's fleeting. So electrons can always move within bonds. If it's useful to the molecule, it's going to sometimes have electrons on one end of the molecule more than the other. It's fleeting, which is why it's not very strong, because it's not a dipole that's always there. It just comes and goes. But when we look at carbons with a lot of carbon and hydrogens, we definitely see these coming into effect. And that's our London dispersion forces. They're weak, but they're additive. So our small molecules like butane have a very low boiling point, which is like butane's a gas. Pentane and hexane, as we increase the number of carbons and hydrogens, we increase the amount of London forces and the boiling point increases a good bit. So it makes a difference even though it's weak. So as we get higher molecular weight, then the boiling point increases. And remember when we're talking about boiling point, we're thinking about, okay, we have a compound, it's in liquid state, so they're fairly close together. For them to boil, those intermolecular forces have to break so they can get gas and completely not interact. The same trends, though, we can see for melting point, but none of these would be a solid at room temperature. But as we get to things that are a solid, again, the solids are held together by intermolecular forces. So the harder it is to break those forces, the more energy it's going to take to melt. Then the more energy it's going to take to boil. Now, when we start getting branching, we actually see less of a boiling point. We can only really compare these that have about the same amount of carbons and hydrogens, though, because the amount of carbons and hydrogens increase London forces. But when we see branching, and all of these have the same, they're all isomers, we see the boiling point decrease because now with the branching, the molecules can't get as close. So there's less surface area where they can interact, and you get less forces. Again, to compare those things without actually having the boiling point, you need to have similar size molecules. The next one is dipole-dipole forces. These are going to be stronger than London dispersion forces because the dipole moment's always there. Oxygen's always more electronegative than carbon, so oxygen's always going to have the electrons closer to it, and it's always going to have a partial negative charge. Carbon's always going to have a partial positive charge. It's not fleeting, so it's going to be a stronger interaction. Same type of interaction, the positive charge of the one carbon is going to be attracted to the negative charge of one of the oxygens, and they are held together. So they can align and have more forces, and therefore they have elevated melting points and boiling points. Hydrogen bonds are not bonds, and they're actually just dipole-dipole interactions. They're just much stronger. And they're the strongest of our intermolecular forces, except for ionic dipole interactions and ionic interactions. So a full charge is clearly going to interact more. But when we're talking about neutral carbon, neutral organic compounds, it's really strong because it has strong partial positive and negative charges, but also because of hydrogen. Hydrogen's small, so they can get closer. because hydrogen is so small. So it's really why hydrogen bonding is where we see it. So because the hydrogen is so small, it can be slips. For something to be able to hydrogen bond, you need a hydrogen bond donor, which is a hydrogen attached to an electronegative atom like oxygen or nitrogen, or fluorine, but what we mostly see is oxygen and nitrogen. And then we need an acceptor, which is a lone pair on something like oxygen or nitrogen or fluorine. For something to be able to hydrogen bond with another molecule of itself, it has to have both acceptors and donors. Though, if something, so NH3 does, H2O does. However, this cannot hydrogen bond with itself, but it can hydrogen bond with water. Because water has a donor, but it couldn't hydrogen bond with itself. So its boiling point would only be affected by dipole-dipole interactions. So only when the hydrogen bonds share electrons will that happen, but it's also additive. The more you have, the more you can have sharing. And compounds that have H atoms that are capable of forming hydrogen bonds are called protic. These are also typically capable of donating a hydrogen through acidity. This brings us to solubility, which again is going to be important later. Like dissolves like. What we're talking about is, do compounds that we're trying to mix with each other solubilize or be miscible? Do they have like interactions? The more like interactions they have, the more likely they will be to be soluble. So it's kind of additive, which is why something like a fat might not be very water soluble, because it has a long carbon chain but also some dipole moments. So you really have to look at it on a case-by-case basis. But in general, polar compounds will mix well with other polar compounds, and nonpolar compounds will mix well with nonpolar compounds. More complex compounds have a bunch of things going on. Okay, this is going to be the last one for today, and then we'll finish this on Friday. So, everything about cyclohexane. Cyclohexane literally only has hydrogen and carbon, so it's only London. Now, we're going to have to make up Friday's class somehow. I'm not really quite sure how yet. Can you guys come earlier on Friday than 12:55? Like it? No?
Aren't you giving the review for our...
At 2:30. After this class. So yeah, we're gonna have to make this up. I'm not really sure how, but I'm gonna try to figure something out. And also work on chapter 3. Yeah. No, chapter 2. I'm sorry. Isomers. Chapter 2. We're gonna try to get through nomenclature and isomers on Friday. Have a good day.